All right, this is our solutions to the first waves worksheet where it's talking about waves. So a transverse wave is one where the medium, the thing that the wave travels through, is displaced perpendicularly to the direction of wave velocity. So if that's a transverse wave, the wave is moving this way, but the medium is moving up and down. That's what it means to be a transverse wave. Now, the way we usually do this, this is a crest, it's the high part. This is a trough, it's a low part. And then a wavelength is any one single wave. So wavelength is from here to here. That's a whole wave. That's a wavelength. Or a wavelength is from here all the way to here. That's a wavelength as well. The idea behind a wavelength is that it's the length of one entire disturbance, not not when we get back to the equilibrium position, but the length of the entire disturbance. And then the amplitude is the height of the wave. It's not from here to here. That's not the amplitude. The amplitude is right there. It's just the height of the wave. This also is an amplitude. It's that measurement there. The rate at which a disturbance is made is doubled. What's the effect on the period, frequency, amplitude, and wavelength? So the rate at which the disturbance is made, that is the frequency. So for us, the frequency is doubled. And since we know that period is equal to 1 over the frequency, if I double the frequency, that means the period is halved. And then we know that the velocity is equal to frequency times wavelength. So the velocity is going to stay the same. There's no change to the medium. There's just a change to how quickly you're shaking the spring, let's say. So the velocity stays the same. So if the frequency is doubled, that means the wavelength has to be halved as well. So if the frequency goes up, the wavelength goes down. That's worth writing. So if the frequency goes up, lambda goes down, so the wavelength is halved. Amplitude is the same. Those are all the changes that happen if we make our disturbance faster. If the amount of energy is doubled, what's the effect on the period, frequency, amplitude, and wavelength? Okay, so good news here. Period, frequency, and wavelength, they're all the same. But if we get more energy, we get more amplitude. So if I put in twice the energy, I'm going to get twice the amplitude. What factors influence the velocity of a given wave? The medium is the only thing that affects a wave. It's the only thing that affects a wave's velocity. A different medium gives you a different velocity. That's how it works. Change the medium, change the velocity. A wave has a frequency of 1500 hertz and a wavelength of 2 meters. What's the velocity? Velocity is frequency times wavelength, so 1500 times 2, that gives me a velocity of 3000 meters per second. A radio wave has this wavelength, and we want to know the frequency given the velocity. Well, velocity is frequency times wavelength. So the velocity is 3000 times 10 to the 8th, and that's equal to the frequency, which we don't know, times the wavelength of 2.94. So we're going to divide both sides by 2.94. And so we get that the frequency is 3 times 10 to the 8th divided by 2.94. And since that's something with scientific notation, we're going to pull up our handy dandy calculator. And so we get 3 times 10, oops, sorry, wrong one. 3 times 10 to the 8th divided by 2.94. We end up with 1.02 times 10 to the 8th meters per hertz. Pretty high frequency there. If the crests are 3 meters apart and pass by a fixed point on a jetty every 2.5 seconds, how fast are the waves moving? Okay, so this thing here, crests are 3 meters apart. The distance between the crests is the wavelength, and this is my period, one wave every 2.5 seconds. So we could say that the velocity is the wavelength over the period, so 3 meters divided by 2.5 seconds. Looking at that wave velocity, we end up getting 1.2 meters per second for the wave speed. And then if we want the frequency, it's 1 over the period, so 1 over 2.5. And we get 0.4 hertz as the frequency for that. And so I think the tricky part about this question is it's just telling you the distance between crests. It's not saying the word wavelength, so you have to look out for that. 3 friends are having a sound race. Bobby creates sound waves with a frequency of 550 hertz in air. Jimmy gives his frequency, and Casey has another one. The speed of sound in each medium is given, and the table racetrack is 100 meters long. Whose sound waves win in the race? So for this, only velocity... Oops, sorry. Only velocity matters. So fastest velocity wins. That's going to be diamond. Diamonds win the race. So that's not one of the ones that we're using, right? So we have air, water, and iron. So iron is the fastest velocity. That means Casey's sound waves win. Calculate the wavelength of each person's waves. Whose sound waves have the highest wavelength? Why does the amplitude of sound waves not matter? It's just an energy consideration. All right, so if I want to calculate each person's sound waves, scroll down so we can see it all. We have Bob. The velocity of Bob's sound waves, because he's in air, is 343 meters per second, and the frequency of Bob's sound waves is 550 hertz. The next person that we have is Jimmy. The velocity of Jimmy's sound waves, because he's in water, is 1500 meters per second, and the frequency of Jimmy's sound waves is 1100 hertz. And then we have Casey. The velocity of sound in iron is 5,130 meters per second. And the frequency for Casey is 225 hertz. Now, if we're going to calculate the wavelength, we've got V equals frequency times wavelength. I'm going to divide both sides by the frequency. And we get that the wavelength is equal to the velocity divided by the frequency. Well, that's what we have here, right? So lambda is equal to the velocity divided by the frequency. So for Bob, that's 343 divided by 550 hertz. So the wavelength for Bob comes out to be 0.624 meters. For Jimmy, the wavelength, velocity divided by the frequency, 1500 divided by 1100. His wavelength for Jimmy comes out to be 1.36 meters. And then Casey, the wavelength is the velocity divided by the frequency, so 5,130 divided by 225. That wavelength comes out to be 22.8 meters. And again, it's definitely Casey who has the largest wavelength. All right, so Heimlich creates continuous waves on a string by flicking the spring with his finger repeatedly. So he's kind of shaking a spring to make it. He makes the following changes in how he creates the waves. And tell me if the velocity, frequency, wavelength, and amplitude increase, decrease, or remain the same. So if he flicks the spring harder, the medium is the same, right? So the velocity is the same. Now he's not flicking it any faster, so the frequency stays the same as well. And if the velocity and the frequency are the same, the wavelength is the same. But if he's flicking it harder, he's doing more work. That means we're going to have more amplitude. So we're going to have an increase in amplitude. He stretches the spring more. Well, that's a change in the medium. So we're going to have an increase in velocity. Now, he doesn't change how fast he's flicking it, so the frequency stays the same. But if I get an increase in velocity, I get an increase in the wavelength, but since I'm not flicking it any harder, the amplitude stays the same. And here's how I want us to think about our little formula here. We get V equals F lambda, and we're tempted to say that V equals F lambda tells me about velocity. That's not a helpful way to write it. I prefer, and this was in the notes, I prefer that you write it lambda equals V over F. V depends on the medium. F depends on the source. So in our little example here, the medium is the spring. If I change the spring by stretching it, that's changing the medium, and that's going to change the velocity. If I flick things more times per second, that's changing the source. And if I don't flick it, if I just flick it harder, that doesn't change any of these things. That does something else. So if I flick the spring more times per second, we have no change in the medium, so we have no change in the velocity. If I flick the spring more times per second, I'm generating more pulses per second. That gives me an increase in the frequency. And then if my frequency goes up down here, because that's on the denominator, the wavelength has to go down, so that's going to decrease. And since I'm hitting the spring just as hard, my amplitude stays the same.